Good morning. I'm Anurup, working in BOSCH Jaipur for the last 24 years, responsible for the facility management. Today, I'll explain the project taken on energy conservation, which is one of the pillars of sustainability and is empowered through digitalization. Normally, we do the projects on the usage side, but this time we have done the project on the generation side of the compressed air with an objective to control the schedule of the running of various compressors what we have in our network and optimize the set points as per the real-time demand scenarios with the least energy consumptions and no interruptions in the air supply to the production hangar, which needs to be maintained within 5.4 plus minus zero point 0.1 bar. So first I will just show you what is our initial working scenarios, how we were operating it. So in the initial scenario, as we see, there were different compressors of different capacities ranging from 500 CFM to 900 CFM, and they are of different makes, Atlas and Kaiser. And all these compressors were basically operated manually based on the initial demands which was there in the shift, and then based on the experience of a worker they are able to change the different compressors once the demand was different. But they don't have any real-time demand capturing scenarios, and sometimes it is very impossible that in between the shifts or in the later end of the shifts when the demands were low because less machines were operating depending upon the production scenarios, they will never come to know, and then the same compressor will keep on running. So it becomes impossible for human to navigate the compressors as per the real-time demand scenario. So what we have done, then we have collaborated with our software division to develop the entire system of this compressors network working on the autonomous way. So once we have discussed with them and set the, you can say, scenarios of working, it requires that we should capture the real-time demand scenarios, and for that we need to install different energy meters, CFM meters as shown, and all these meters then has to basically communicate. So we started getting all these data in the individual panels, and then when we interacted with OEMs, how we can read the internal data of the compressors so that we can read it, and if possible how we can write it. So what has really happened, that the real-time demand starts getting captured through the entire network systems. It goes into a hub. So both the compressors gets into one hub. Through one hub it goes into our edge gateways, and then from that edge gateways it goes into a cloud, and from this entire cloud these data can be fetched for the portal working, and then for the worker who is available in that particular zone, in that particular area, can also visualize it through this entire system, as you can see on the dashboard. Earlier he has to monitor it at the, you can say, compressors, he has to go and see, but now he can just simply see once in a while in a dashboard how things are working. So in the dashboard also we can see what is the real-time demand scenarios, what is the pressure maintained, how are things moving, what are the internal parameters of the compressors. So what we have done, as you see, that normally an average consumption of my plant is 44,000 units per day. Utilities consumes 20% of our consumption, and the compressors normally consumes 50% of that. We have done the initial loading analysis in terms of histograms of all the compressors. Since we have one fixed type of a compressor and then three variable types of compressors, so we have seen that the loading is maximum for the LP6 compressor, which is a variable compressors, and is normally loaded to 60% of its capacity. So this is all which is being available through a histogram analysis for the initial way of working. And then normally we are loading a fixed type of compressors, which by its nature sometimes takes 100% of energy, close to 100% of energy. So then what we have done, since we have shown all the meters, so we have done the scatter plot analysis. We have done the scatters plots for the different compressors working in a pair. So we can see that for an average demand of 450 CFM, which compressor takes the least energy. So we can see this blue band compressors taking least energy, which is LP3 and LP6. So this is the first insight which came through this entire scatter plot analysis. Then what we have done, we have prepared a cause and effect diagram considering the power as one of the factor and how power is influenced by the other elements of the compressors. So wherever we see a value more than 0.7 in a positive direction shows, so this is the second insight which came to us. So this becomes a condition based monitoring for us. Till now we were doing a time based PMI. So now we have moved from time based PMI to a condition based PMI. So now we can see how this entire flowchart has been prepared, that we have a train model which takes the samples, it checks the demand, it checks the sensors pressure, header pressure, compressors health status, and based on the model being trained, it gives the different sets of, you can say, commands to the compressor controller how it needs to be operated. So now my colleague Mr. Akshay will explain all about the models.
Hello everyone, good day to all of you. The objective for us to build a model was to make it proactive in nature so that the compressor bank is always ready to meet the ever-changing demands of the manufacturing plant. This makes the model a bit different from a conventional PID control system. A PID control system reacts to the situation, and by the time the command of a set point change or change in compressor priorities relate to the compressors, the compressed air demand scenarios would have already changed. The model that we have implemented estimates time ahead the scenarios of compressed air demands and readies the compressor bank to meet the dynamically changing demands. Before we deep dive into how the model is designed and implemented, I would also like to quickly focus on the kind of data that is collected. So this data includes the compressed air demand, the header pressure, the set points that are set on each compressor, the working status or the fault status of the compressors, which is also derived in turn by checking the health parameters of individual compressors, which are also being recorded. As we all know, the sensor data will have noise from time to time. In order to feed the right information to the trained model, the data first passes through a data cleaning filter. So for this data cleaning filter, we use the fourth moment of statistics, or as we all know, it's also called as kurtosis. So we use kurtosis to identify the outliers in the data. And these outliers which are detected in real time are eliminated, and only then the data is fed to the trained model. Let us now deep dive into the working of the model design and the implementation. Now we also have some operating boundaries or constraints in which the model has to operate. The real-time compressed air demand has to be met in real time, and the header pressure has to be maintained at 5.5 bar or at least 5.5 bar. Now the compressor combinations to operate depend on the individual rating of the compressors, and the set points that have to be set depend on the real-time header pressure situation. So for this, we have developed or defined a class of operation table for various demand scenarios. The model selected then has to classify the demand scenarios in real time based on this class of operation table. In order to estimate the immediate time ahead scenarios for compressed air demand for the next 8 minutes, we calculate the trends in compressed air and header pressure for the previous 8 minutes. For these estimated trends for the next 8 minutes, we had to use a decision tree based model, as this is in the realm of a classification use case. The model was trained on historical data set of 3 months. That was the data that was recorded in this edge gateway. Now, there were scenarios that were hypothesized but had never really occurred in this historical data set. For such hypothesized scenarios, simulated data was introduced in this training data set. This was very important so that the trained model was ready for any scenario that would occur in the future for this compressed air demand scenarios. The training results for this model were quite positive. The model was 100% accurate in selecting the right combination of compressors. The model was 99.7% accurate in selecting the right set points for the individual compressors, which was 6 errors out of 2000 testing samples.
So also now I would like to tell you that how this entire system is seen in terms of a navigation page. So this is a portal which has been worked it out. So we can see that on a particular day, on a particular time in the compressor bank, as the compressor demand is increasing, so similarly the pressure has increased. So how we can reflect these things in the compressors? We can see one of the compressors, as the demand is increased, the set point also has increased. So this is how the autonomous changes in set point is happening as per dynamic load. And what has really happened with this entire thing, we are able to save 108 megawatts of energy, which is somewhere 78 tons of CO2. And for all the hardware configurations, we have invested somewhere close to 3 million in terms of software development, in terms of real-time communication. So the payback is 3.8 years. And this is a step towards thinking utilities, what we call as a control and command center. So with this, also what we have done, we have also applied as an invention report, and this is how we are moving it forward. Thanks.